to evaluate the impacts of different residential development styles within the urban forest of Charlotte, North Carolina. And this is a project that I worked on throughout my senior year at UNC Charlotte through the North Carolina Space Grant Program. And we actually got this published in the form of an academic article this past summer in Landscape and Urban Planning. So yeah, if you need to know any more details, you can check that out or ask me anything. So urban forests can provide a lot of benefits to a region and its residents. It serves as a natural filtration system for water, air, and sunlight, and overall it creates a more healthy, attractive, and sustainable environment for people to live in. However, trees are highly affected by human activities. So changes in land use when a region becomes developed can alter the natural carbon cycle. Therefore, cities need to provide adequate space for trees to mature and reach their full carbon storage levels that they have the potential for, and in turn offer that much more benefits to the city. And this is shown to benefit cities in a lot of ways, but I believe in 2010, Charlotte estimated that they received a $3.25 return for every dollar that they spent on tree care, which is pretty amazing. So because of the problems that arise when pairing the built environment with the natural landscape, we want to understand how different residential development styles affect the health of trees, and we represent the health of trees in the form of carbon density. So this is the study area. Our study boundaries are actually all of Mecklenburg County. I'll often say both Charlotte and Mecklenburg County because Charlotte's influence stretches beyond the county boundaries. Charlotte's primarily made up of secondary growth forests from what it was previously agricultural lands, and the main tree species are oak, hickory, and pine trees. So these are the data that we use for this project. We have small footprint LiDAR with a 1 meter resolution and aerial imagery with a 1 meter resolution. So we're dealing with relatively high resolution data, and that allows us to detect details on the ground while avoiding a lot of field work that could be very time consuming and costly. But some of the field work that did have to be done was in the form of these 75 field plots, which was they'll be used as validation in our first set of models that I'll talk about here shortly. So these are the general methods of our project. We take the data that I talked about previously and do some pre-processing that I don't have time to talk about today. But the two main parts I'll talk about are the first phase, the modeling of the above-ground biomass across the county, and then neighborhood carbon density modeling to see how these development patterns are affecting the trees. So in this first phase, we're trying to figure out what combination of LiDAR metrics can best be used to predict biomass across the entire county. And if you're not familiar with LiDAR metrics, they're basically a set of statistics based on the tree height measurements taken by the LiDAR remote sensor. In this plot level biomass estimate, this is calculated from the 75 field plots that I talked about previously through allometric equations. And throughout the process of developing these models, we actually developed 3 separate models for deciduous, evergreen, and mixed forest stands. And this is shown to benefit the accuracy values as opposed to developing a single model across all 3 forest types. These forest types they have many variations in their structure. So to develop these models, we first had to figure out what LiDAR metrics can work best. And to do that, we first did some literature review to figure out a narrow list of LiDAR metrics because the program that we use is called Fusion. developed by the U.S. Forest Service, and it calculates a lot of LiDAR metrics. So we came up with this narrow list of LiDAR metrics seen in the table, and these metrics are some of the most commonly used LiDAR metrics for predicting above ground biomass. And following that, we then did extensive testing on different combinations of variables to figure out what was best. And throughout this process, we considered both logarithmic and Box-Cox transformations. And these transformations are simply to create a more linear relationship between these LiDAR metrics and the biomass on the ground. So these are the three final biomass prediction models that we came up with. A few things to notice across these three models. The deciduous model worked the best using a Box-Cox transformation on the dependent variable while using a logarithmic transformation on each of the independent variables. The evergreen model worked at the best using no transformations at all. The mixed model worked best using a logarithmic transformation on both the dependent variable and each of the independent predictor variables. Another thing to notice is the variation in accuracy values across the three models. Evergreen has the highest R-squared value because evergreen trees have the most predictable structure as opposed to deciduous and mixed forest stands. So, using these biomass prediction models, we then modeled biomass quantities across the county at a 20-meter resolution. And then we did a simple conversion from above ground biomass to carbon to facilitate comparisons to other literature. So by doing that conversion, we were able to compare Charlotte to Atlanta. We have a slightly lower average carbon density than what is found in Atlanta. And the carbon storage throughout the county amounted to 3.8 million tons, and this has a value of over $298 million. So now we have these carbon quantities mapped throughout the county, and we want to figure out what characteristics of the neighborhood are having positive and negative impacts on this on the health of trees. So to do this, we first had to figure out how to divide the county into neighborhoods, and we use what's called a neighborhood profile area, which is pretty common in the Charlotte area. It's used by the Charlotte Quality of Life Study, and these are based on census tract geographies. And we first had to narrow this list of neighborhoods down a little bit. So our focus is on residential neighborhoods. So we used a threshold of 75% and excluded any neighborhood that had less than 75% residential zoned land. Then we had to break the neighborhoods into different categories because depending on where you are within the city, neighborhoods are going to vary greatly with their structure and how developed they actually are. So we broke the neighborhoods down into 4 different categories based on percentages of built lands or impervious surface, which was calculated through the classification that I didn't have time to talk about here. But the 4 categories we came up with were less than 15% built lands, 15 to 25% built lands, 25 to 40% without built lands, and anything more than 40% built lands. And using the carbon quantities, we then calculated a carbon density across each of the selected neighborhoods, which will be used in our next set of models that I'll talk about here in a second. So then we had to figure out how are we going to quantify the structure of the landscape and different characteristics within the landscape. And to do that, we used what's called a landscape metric, which is calculated by a program called DragStats. And once again, it's a set of statistics, but the 2 main types of landscape metrics that we use within this study are a class level metric, which is based on each of the individual classes within the neighborhood. So there's a set of landscape metrics for each of the classes seen here for built, evergreen, deciduous, etc. And then there's a set of landscape metrics, which is a set of statistics based on the neighborhood as a whole. So yeah, using these landscape metrics representing the development styles and the structure of the neighborhood, we want to figure out what aspect of that neighborhood structure is affecting the neighborhood carbon density, aka the health of trees within the neighborhood. So once again, we're going to use regression models to figure out what aspects of the landscape structure are affecting this carbon density. By doing this, we're able to so this is the first model that we came up with for the less than 15% built lands. This is mostly, these neighborhoods were mostly categorized by sparse development, mostly undeveloped lands with patches of development throughout. And within this set of models, we found that as the diversity within the neighborhood increases, then we'll have a negative impact on the health of trees. Also, as amounts of built land increase, the carbon density will decrease as we would expect. And as the forests become more aggregated within the neighborhoods, then the carbon density will increase. For the second category of neighborhoods, this is represented by suburban style development with small to medium trees within the yards of homes. And within this category of neighborhoods, we found that once again, as the diversity in these neighborhoods increase, then the carbon density or the health of trees is likely to decrease. Also, as deciduous patches become more evenly distributed across the neighborhoods, carbon density will increase, and as water patches become more aggregated in these neighborhoods, we'll see an increase in carbon density. In our third category of neighborhoods, 25 to 40% built lands are found in these neighborhoods. Within this set of models, this one was a little bit different than the other ones. But we found that once again, as built land increases in these neighborhoods, the carbon density will likely decrease. As open land decreases, carbon density will also decrease. And finally, as the bare soil distribution becomes more even across the neighborhoods, then the carbon density will likely decrease. And then in our fourth and final category of neighborhoods, representing the most developed neighborhoods of Charlotte, these neighborhoods were classified by mostly mixed-use residential with a lot of apartments and townhomes. And once again, within this model, we find as the diversity increases within these neighborhoods, then the carbon density will likely decrease. And also similar to some of the previous models, as the aggregation of forests within the neighborhoods increases, the carbon density is likely to increase as well. So, some of the things we saw in common across the four models was mainly the aggregation of forests. So really, the less fragmentation that we have within the forest when it comes to residential neighborhoods, then the healthier the trees are going to be, because they have all the room in the world to grow. Nothing is affecting them. So overall, I think the methods with large volumes of the world population moving into cities, we need to overcome the problems that arise when pairing the built environment with the natural landscape. And I believe these methods can offer a chance for us to understand that a little better. Also, these methods are able to facilitate urban planner to establish different methods of residential development with respect to their community planning techniques. Thank you.
We've got time for some questions. Do we have some questions for Chris?
Yes, sir.
I was interested to notice in the very first part of your analysis that for evergreens you were using 5th percentile of height as the predictor.
That's right, yeah.
Is that the lowest 5th, like the low 5th? That's close to the ground 5th, not 5th from the top.
That's right, yeah.
So I would have thought, I was surprised to see that. I would have thought higher, conifers tend to be tall. It seemed like a low height value to be the best predictor for evergreens.
In the residential areas, a lot of people put evergreen trees in the yards of their homes, and they don't tend to get that big. So that 5th percentile is kind of representing that understory.
Junipers and stuff.
Yeah, that's what most of this is developed land, so it's not so natural.
I see. So how high is 5th percentile, like off the ground?
I'm not exactly sure about that.
Other questions? All right. Thank you very much. And you can make sure Kim Casey is